Chapter 11, Generic Business Jet with Composite Stiffness, we call it GBJ-ST, using Lagrange shape function design variables. The purpose of the sample case is to optimize the GBJ-ST structure for minimum weight design using Lagrange shape function design variables, subject to flutter constraint using Decal Lamp, strength constraint using Decal FTM, panel buckling constraint using Decal BK, column buckling constraint using Decal BKE, and stiffness crippling constraint using Decal CRIP, and stiffness ratio constraint using Decal BK, and laminate composition constraint using Decal Lamp. We also want to show how to model the composite stiffness by the P-bar-ST property car and then impose the crippling constraint to the flange and web of the stiffness. We want to show how to impose the stiffness ratio constraint, KR, between the stiffness and their attached wing skin panels. We want to demonstrate how to perform a two-step optimization approach to circumvent the convergence problem due to the inclusion of a composite laminate composition constraint, Decal Lamp. The wing structure model of the GBJ-ST is modified from the wing structure model of GBJ by removing the 4 middle spots from the GBJ model. So the GBJ model has 6 spots. So we only keep the front spot and the rear spot, and they are not subjected to redesign. Then we remove the 4 middle spots. Along each removed spot, and we add 13 C-bar elements to the upper and lower skin to each C-bar represents a stiffener. So the total number of added C-bar element is 13 times 4 removed spots and times the upper and lower skin is 104. Each C-bar element represents a composite stiffener with a T-cross section that is specified by the P-bar-ST property car. The flange and the web of each composite stiffener are made by a 10-layer laminate of plus minus 45 degrees. The 0 degrees apply and 190 degrees apply, and it is symmetric about its midplane, and that is specified by the PCOM property car. The dimension of all T-shaped stiffener are the same, of which the width of the flange is 8 inch. The height of the web is 1.8 inch. So this is the P-bar ST, which is referred to by the C-bar element, and we specify a T-cross section, and for the web it's 8 inches, and it refers to a PCOM car, which lists out those 10 layers, and then the height of the web is 1.8 inches, and it refers to another PCOM car, which lists out the same 10 layers of composite laminate. The aerodynamic model of the GBJ can be directly adopted for GBJ-ST. Spline flutter analysis and the flutter constraint between the GBJ and GBJ-ST are identical. However, instead of specifying only one 4G pull-up trim condition to compute the trim loads for GBJ, and 2 trim conditions for GBJ-ST are specified. The first one is a 3.75 G pull-up condition, and the second is a -1 G push-over condition. The first trim analysis can induce compression on the upper skin, and the second trim condition can induce compression on the lower skin. 2 sets of trim load are applied to the wing skin and stiffness for panel buckling, stiffener buckling, and crippling, as well as strength constraint evaluation. All panel buckling of the wing skin column buckling and the crippling of the stiffness, and the strain constraints are subjected to the two sets of trim loads. To prevent the stiffness from column buckling problem, the following decon BKE cars are specified for those C-bar elements of the stiffness. So decon BKE with a set ID. This set ID is referred to by decon equals case control command and apply to the bar with the C-bar ID here. And this is simply support the boundary condition. A lower bound is 1. To prevent the stiffness from crippling problem, decon car are specified. Because the P/ST cars define the T shape of each stiffness that consists of a flange and a web. Each stiffness requires 2 decon car to prevent its flange and web from crippling problem. In addition, one more decon car is needed to impose the column stiffness crippling stress constraint for each stiffness. For instance, for the C-bar element with ID 3121, the following 3 decon car are specified to impose the crippling constraints. So again, 1020 is a set ID which is referred to by the decon equals case control command applied to the bar, and applied to the with ID 3121. D1 is applied to the flange, and D2 is applied to the web, and all is to impose the column stiffness crippling stress constraint. To prevent the skin panel from buckling problem, the decon BK car are specified. So again, the set ID is 1021 and applied to the quad 4 element. This ID and is a simply supported boundary condition, and lower 1 is a lower bound and impose the buckling constraint subject to 2 sets of trim loads using the method documented in this Air Force report. And why the panel buckling problem, the stiffness column buckling problem, and the stiffness crippling problem can be prevented by the decon BK, decon BKE, and decon crip cars respectively. These constraints are not sufficient to prevent the whole stiffness panel bay buckling problem. The stiffness panel bay is defined by for example, in this shade area, it is bounded by the leading edge spar and trailing edge spar, and between 2 ribs. Inside this panel bay, we have a several stiffness. So this whole bay may buckle together. And this problem can be prevented by imposing the stiffness ratio constraint to the stiffness using the decon KR car as the one shown below. So decon KR, the lower bound is 1, and the C bar with ID 3242, L play and R play is the panel skin C-bar element which is attached to this C bar on the left hand side and on the right hand side. We leave it blank because ASTROS can automatically find out who are the 2 C-bar force attached to this C bar elements. And we use method equal 2, and the width is the distance between 2 C bars. The A is the width of the panel bay. 148 is the length of the panel bay, and because the entry method 2 in the decon KR car, the entry width A, B, and PB. PB is a post buckling factor. Default is 1.5. Must be specified. The shear area shown in this figure, bounded by the front spar and rear spar, and two ribs define a stiffened panel bay. To impose the stiffness ratio constraint of the CBAR element with ID 32445 within this stiffened panel bay, the method to calculate the value with A and B is shown in this figure. So this stiffness ratio constraint, that means it will the ratio be the bending EI of the CBAR and the bend the stiffness of those two attached C-4. The stiffness of the CBAR and the stiffness of the two C-4 element, and they must be within upper and lower bound. Okay, so this if they satisfy this stiffness ratio constraint, it can prevent the whole panel bay from buckling problem. The next is the stringent laminate composition constraint, Decal Lamp. In the GBJ-ST model, all P-con property cards for the wing skin and the stiffness consist of a 10-layer laminate. The same 10-layer laminate as those of the stiffener. If we require, say, we want the thickness of the plus minus 45 degree layers must be within 30 to 50% of the total thickness of the panel for the wing skin, and also for the stiffener. The 0 degree plies, its thickness must be within 30 and 50% of the total thickness of the panel of the skin, and also for the stiffener. The 90% ply, its thickness must be within 15 to 25% of the skin and of the stiffener. So stringent laminate composition constraints are imposed on the wing skin as well as on the flange and the weft of the composite stiffener. For the plus minus 45 degree layer in the wing skin, Decal Lamp card can be used to impose this laminate composition constraint. So we have a Decal Lamp. The lower bound is 30, and the upper bound is 50, and 1290 refers to apply list card, which we list the first layer and second layer, the 9th layer and 10th layer, because this is the 1 and the 10 are the positive 45, and 2 and 9 are the negative 45. Those thickness divided by the total thickness must be within 30 and 50%. And this 1000 and 2000 refers to the element list card. The 1000 lists the IDs of the C-card for element on the wing lower skin, and 2000 lists out the C-card for IDs on the upper wing skin. Why the ply list card with ID 1290 links the first, second, 9th, 10th layer together, and is referred to by about Decal Lamp card. Thus, the thickness of the plus minus 45 degrees layer must be within 30 and 50% of the total thickness of those C-card for element listed in the element list cards with IDs equals 1000 and 2000 for the wing skin. The similar Decal Lamp card are defined for the 0 and 90 layer of the laminate. So we can use Decal lamp. For example, if you want to impose the 90 degree, the 90 degree is the fifth and the sixth layer. So we can refer to another ply list card, and we list out the 5 and the 6, and so that will impose and the lower will be 15, the upper will be 25. So we can impose the thickness, the laminate composition constraint for the 90%, 90 degrees layer. To impose the composite composition constraint to the flange of the stiffener, similar Decal Lamp card are specified, except referring to the element list that lists the C-bar IDs of the stiffener. To impose the Decal Lamp to the web of the stiffness, the layer number listed in the ply list card must be increased by the number of layers of the flange. So the layer index, our 10 layer composite in the web start from 11 to 20. So so if we want to impose the Decal Lamp for the plus minus 45 degree, the ply list card must for the web must be 11, 12, 19, and 20. And thus refer to the C-bar elements IDs on the lower wing skin. This refers to the C-bar element IDs on the wing upper skin. Imposing the lower and upper bounds of the laminate composition constraint Decal Lamp may reduce the physical domain of the design space. And the figure shown here is a two design variable design space V1 and V2 with the lower bound and the upper bound of the laminate composition constraint along with other constraints. So this is the objective function, which is decreased as V1 and V2 decrease. And we have in this two-dimensional design space, the laminate composition constraint represents two straight radial lines from the origin. And therefore, the physical domain is bounded by those two lines and other constraint if we have other constraint here. So the physical domain is shown here. If the initial design variable V1 and V2 are located outside the physical domain, the optimizer may have a difficulty to move the design variable into the small physical domain. So to circumvent this problem due to the inclusion of a laminate composition constraint, it is suggested to use a two-step optimization approach. Step 1, defining the initial thickness of all layers in the laminate that satisfy the laminate composition constraint. Then we removing the Decal Lamp and link all the layers into one design variable and performing the optimization with other constraints. Step 2, using the optimized layer thickness of step 1 optimization as the initial thickness of step 2, performing optimization with the Decal Lamp constraints and with other constraints. So first, the all Decal Lamp for the step 1 optimization, all Decal Lamp cards are removed. Next, the initial value of all layers in the PCOM card should be within the lower and upper bound of the laminate composition constraint, so that the initial thickness of all layers satisfies the laminate composition constraint. Finally, each PCOM card should be defined as one design variable by linking all layers in the PCOM card together. For two design variable optimization problem, the design space of step 1 is shown figure below, and where the equation V2 equals to K times V1 links those two design variables into one design variable with the selected value K, so that V2 divided by V2 plus V1 and V1 divided by V1 plus V2 satisfy the laminate composition constraint. So we only have one design variable, and by specifying a large value as the initial thickness of the one design variable, the initial structure should satisfy all other stiffness and loads related constraints. So it is within the feasible domain. So the initial design variable is located within the feasible domain. And with a relaxed optimization convergence criterion for optimization, for example, the convergence limit equals 1, the in the optimized solution control command, the optimizer can easily reduce the weight of the structure by decreasing the design variable along the line defined by the equation V2 equals K times V1 until it finds a rudimentary optimized solution that satisfies the relaxed optimized conversion criterion. So in the step 2 optimization, all layers in the PCOM car should be defined as individual design variable with their initial things being obtained from the step 1, so that the initial design satisfies the Decal Lamp. And so the initial design a variable of V1 and V2, they are located in the feasible domain. So for two design variable problem, the design space of V2 with all constraints, including the laminate composition constraint, is shown in this figure. Thus, the initial design variable are located in the feasible domain bounded by the laminate composition constraint and other constraints, except the structure weight is not a minimum weight solution because the relaxed optimization convergence criterion used by step 1. The minimum weight solution can be determined by step 2 optimization with a tightened optimization convergence criterion. For instance, convergence limit equal to 0.05. So in step 1 we use 1, in step 2 we use 0.05. So the optimizer can move the design variable until it finds a minimum weight solution. And so for the GBJ-ST, for the step 1 optimization, in the optimized solution control command, we say convergence limit equal to 1. And also the constraint tolerance are relaxed by specifying the following two MP param car, and we relax the CT and the CT mean, where those relaxed constraints are very relaxed optimization convention criterion, so that the step 1 optimization can converge rapidly, except the result is only a rudimentary optimized solution. For constraint, we include the flutter constraint, panel buckling constraint, column buckling constraint, and the stiffness crippling constraint, and the stiffness ratio constraint. And but the Decal Lamp, the laminate composition constraint are excluded. However, because the 10 layers specified in the PCOM car automatically satisfy the laminate composition constraint, and all 10 layers are linked together as one design variable. In the step 1 optimization, the laminate composition constraint is invariant during the optimization iteration. So, because we specify the thickness of the 10 layer, and each layer is 10% of the total thickness. So for the plus minus 45 degrees layer, we have 4 layers, so it's 40%. That is within 30 and 50% of the total thickness. For 0 degree ply, we have 4 layers, so also satisfy 30 within 30 and 50% of the total thickness. For the 90 degrees ply, we have 2 layers, so it's 20%, and it's within 15 and 25% of the total thickness. Then we link all the 10 layers together as one design variable. So during the optimization, the optimizer may change the total thickness of the laminate. However, the laminate composition is invariant during the optimization iteration. Therefore, the final optimization design also satisfies the laminate composition constraint, even without the laminate composition constraint being explicitly imposed. And so the 10 layers specified by the PCOM car of each sequence 4 on the wing lower skin and upper skin are linked together by the DESVARS car. So this DESVARS S and this refers to the playlist car. We list out all the 10 layers, and the minimum is 0.001, and the maximum is 0.05, and each layer the initial thickness is 0.05. So all the 10 layers, and this guy override the thickness specified in the PCOM car. So in the PCOM car, all 10 layers will have a 0.05 inch as the initial thickness. And so this one link all 10 layers together to be one design variable, and this one refers to the shape car, and it refers to the shape car with ID 10,001. That is the same as that of a GBJ. The shape of the car for the stiffener are adopted from those 4 removed spots of GBJ, where 4 Lagrange control points are selected for each spot. Because each stiffener refers to 2 PCOM car for the flange and web, and each PCOM property cars has 10 layers. The total number of layers of each stiffener is 20. The first 10 layers that belong to the flange are linked together by the DESVARS car, and it also refers to the same ply list to link all the 10 layers of the flange together. And the initial thickness of each layer is 0.15. So on the wing skin, the initial thickness of each layer is 0.05, but for the stiffener, it is 0.15. The DESVARS S for the web that has 10 layers, 11 to 20. So this one it refers to the ply list car, at least 11 to 20, that links all the 10 layers on the web together as one design variable. Again, the initial thickness is 0.15. The Lagrange shape function of the wing are the same as the GBJ, of which 21 Lagrange control points are selected on the wing upper and lower skin. Therefore, the total number of DESVARS S for the wing upper and lower skin is 21 plus 21 equal to 42. For the GBJ model, because we have 4 layers, and each layer is a design variable, so the total number of DESVARS for the GBJ is 42 times 4. But for the step 1 optimization of the GBJ-ST, because we link all 10 layers together so that they become one design variable. So that 21 control points on the wing upper skin. So we have 21 DESVARS S, and we have another 21 on the lower skin. So we have another 21 DESVARS S. Because 4 Lagrange control points are selected along each spanwise stiffness to replace the removed spot, and each stiffener has a flange and web. The number of DESVARS S car along each spanwise stiffener attached to the wing lower skin is 4 times 8, because each one we have a flange and web. So one for flange, one for web. Since there are 4 sets of spanwise a stiffener attached to both upper and lower wing skin. The total number of DESVARS S is 8 times 4 times 2 is 64. So this 4 is a 4 span-wise stiffness. This 2 is 1 for upper, one for lower wing skin. Therefore, the total DESVARS S of the GBJ-ST is 106. The entry V init 0.05 specified in the DESVARS S for the wing skin overrides the initial thickness of each layer defined in the PCOM card. We define 0.05, but now the initial thickness of each layer in the PCOM card is 0.05. Thus, the initial thickness of all layer of the wing skin is 0.05. The initial thickness of the stiffness layer is 0.15 because the V init is 0.15 specified in those DESVARS S for the stiffness. Specifying thicker layer of the stiffener than the wing skin attempt to increase the moment of inertia of the stiffener, namely the C-bar, and so that the initial structure can nearly satisfy the stiffness ratio constraint. So we want to increase the EI of the C-bar, and so it's stronger. So compare the EI to the EI of is attached to the C-4 is satisfy the stiffness ratio constraints, Decal KR. Because the large initial thickness of all layers, so the total thickness of the wing skin actually is 0.5 inch, and the total thickness of the stiffener is 1.5 inch because we have 10 layers. All stiffness and load related constraints such as flutter, strain, panel buckling, stiffener buckling, and the crippling constraint can be satisfied by the initial structure except the stiffness ratio constraint, DHKR. This because the stiffness ratio constraint is the stiffness ratio between the stiffener and its attached skin panel, which is independent of the load. This is shown in the first optimization. You can see the positive constraint value, meaning the constraint are not satisfied. So this all belong to the stiffness ratio constraint. Thus, during the optimization iteration, the optimizer attempts to satisfy the stiffness ratio constraints, which while reducing the weight. A converging solution is achieved by the optimizer using 11 iteration, and the convergence history is shown below. Then the objective of the step 1 optimization is to generate the optimized design variable that can use as an initial design variable for the step 2 optimization. This optimized design variable are output in terms of the DESVARS cost and in the punch file. So we punch out the final design value of each DESVARS S. So to define the design variable and constraint of the step 2 optimization for GBJ-ST, for step 1 optimization, all 10 layers in each PCOM card are linked to be one design variable. So as the one shown here, and the thickness ratio of the plus minus 45, 0, and 90 degrees layer are defined in such a way that they satisfy the namely composition constraint. For step 2 optimization, the plus and minus 45, 0, and 90 degrees layers are linked into 4 design variables. So layer 1 and layer 10, we link them together to be one design variable, and 2 negative 45 layer are linked together as the second design variable. Those 4 0 degree layer are linked together as a third design variable. The two 90 degrees layers are linked together, together as the fourth design variable. The initial value of the design variable of those layer for step 2 of optimization are taken from the punch file generated by the step 1 optimization. Constraints included in the step 2 optimization are those of step 1 plus the laminate composition constraint, namely Decal Lamp. To define the design variables for the 45 layers in the pecan car of the wind skin, and the following playlist protocol for the 45 degree layers, and we have applied a list with the ID 110, and we link the first layer and 10th layer together. For those sequence elements on the lower wind skin, 21 decibel S for those 21 Lagrange control points are specified. This decibel S car refers to 21 shape car to define the Lagrange bilinear shape function. Each decibel S car refers to the playlist car with ID 110 to link all 45 layers in each pecan property car into one design variable. The initial value of those 21 decibel S car are taken from the punch file. This is the punch file, which is the decibel S on the control point for the wing lower skin, and this the optimized thickness of step 1. So for the step 2, and we specify the initial thickness, and this one this one is at a grid point 62. So this at a 62. So this the thickness, and this is at a grid point 66. This is at 66. So we take this thickness 91. We take that one, and this refers to the shape car. Okay, so the minimum is 0.001, maximum is 0.5, and it refers to the playlist car to link 1 and 10 layer together for the 45 degrees. Of the wind skin. And the 45 degrees layer in the pecan car of the stiffener for those CBAR element attached to the lower wind skin. 16 decibel S car for the flange of the stiffener are specified, because now we have 4 design variable. We have a because we have because we have for 1 2 because we have a let me see, because we have a 1 2 3 4 control points, and each control points we have 4 design variables. So we have 16 decibel S for the flange of the cylinder are specified, with entry V init being taken from the punch file generated by the step 1 optimization. The shape car of each decibel S is the same as the ID of the corresponding decibel S in the punch file. So this is 77, 81, 90, and this is a stiffener on the wing lower skin. So we go to the punch file, the flange of the stiffener on the wing lower skin. So the value is 77, 81, 99. The value is 0.0049 and 0.0345. So it is 0.049, 0.0345, and so on. Cylinder 16 decibel S refers to the 45 degrees are defined for the flanges of the stiffener on the wing upper skin. This is for lower wing skin. Because the P bar ST property car of each stiffener refers to two pecan car, and both pecan car specify the same 10 layers laminate. The layer number of 45 degrees in the web is 11 and 20 for the 45 degrees layer. And so the ply list car is defined like this. This is 16 decimal S car for 45 degree layer of the web of the stiffener as attached to the wing lower skin are shown here. So is the degree that's the 45 degree on the wing lower skin web. Okay, let me see. For the web on wing lower skin, the wing lower skin, the web, so the thickness is 0.1, 0.06, 0.11. So 0.1, 0.06, 0.11. And it refers to the supply race car, so link 11 and 20 layer together for the 45 degrees layer as a one design variable. Similar 16 decimal S cars for the 45 degrees are defined for the web of the stiffener on the wing upper skin. So the total number decimal S for 45 degree layer for stiffness is 64. And then we can define design variable for the negative 45 degrees, 0 and 90 degree layer in the pecan car for the wing skin and the stiffener. For the negative 45, 0 and 90 degrees ply in the pecan car, the following ply list car are referred to by the decimal S for the wing skin flange of the stiffener. So this is negative 45, 2 and 9, and this is 0 degree apply 3, 4, 7, 8, and this is 90 degrees apply 5 and 6. For those sequence 4 on the wing skin, the decimal S for each layer. So this is for negative 45. This is 0 degree layer and 90 degree layer. They have the same thickness. Okay, so because they are at the same grid, so which is 62, and that is from the punch file. It is 0.011. The web of the stiffener, the ply list count for those three layers must be increased by 10. So because the layer index for the web is increased by 10. And the total number of decimal S for all positive, negative 45 degrees and 0 degrees, 90 degrees layer on the wing skin is 168. The total number of decimal S cars for all positive, negative 45 degrees, 0 degrees, 90 degrees layer on the stiffener is 356. So the total number of decimal S is 424. And then after we define the step 2, the design variable for the step 2 optimization, and we change the conversion limit to 0.05, and so we tighten the optimization conversion criterion, and for the step 2 optimization, so that a minimum weight design can be obtained. Because the tightened conversion criterion specified by an optimized solution control command, the optimizer takes 46 iterations to achieve an optimized solution. So the converging history of the step 2 optimization is shown here, following that of the step 1 optimization. And then we look at the thickness distribution along the spinwise stiffener, and we found out this thickness distribution is smooth because we use the linear shift function, and we have 4 Lagrange control. Then we look at the thickness distribution along the spinwise stiffener, and we found out this thickness distribution is smooth because we use the linear shift function, and we have 4 Lagrange control point along each spinwise stiffener. So this is for flange on the upper, the web on the upper skin. This is a flange on the lower web on the lower skin for the 45 degrees layer. This is for negative 45 degrees layer. This is for 0 degrees layer. This is for 90 degrees layer. You can see, and this is the spinwise stiffness near the wing leading edge. This is the near the wing trailing edge, and we have 4 sets of spinwise stiffness. So you can see that they are all the thickness distribution are all very smooth. And then we look at the thickness distribution on the wing upper skin. Also, there's 45, negative 45, 0, and 90. They are very smooth. And the similar thickness distribution among 45, negative 45, and 0, and 90 degrees layers are due to the laminate composition constraint. And so the positive and the negative 45 and 0 degree must be within 30 to 50%, and the 90 degree must be within 15 to 25% of the total thickness. The thicker panel near the wing wing tip. Okay, you can see the thickness near the wing tip become thicker. Probably is due to the stiffness ratio constraint. The thicker stiffness, thicker stiffness near the wing tip leads to thicker panel, because if you look at the stiffener thickness, and near the wing tip, the thickness increase slightly, and so therefore, in order to satisfy the stiffness ratio constraint, the thickness of the skin panel near the wing tip also become a little bit thicker. And that's the thickness of the four layer on the wing lower wing skin, and you can see the thickness of the wing lower skin is thinner than the upper skin, and this because the buckling constraint is due to the compression loads on the upper skin due to the 3 and 3.75 G pull-up condition, and the skin buckling constraint on the wing lower skin is due to the compression from the 1.5 G pushover condition. And so the compression load is less than the upper skin. Therefore, the thickness is thinner than the upper skin. And we look at the VG and VF on the diagram, show the flutter is not active constraint. And we check the laminate composition constraint, and this is on the wing skin, and this is the 0 degrees ply. And this is the plus and minus 45 degrees ply. You can see that within 30 and 50%. And this is 0 degrees ply. No, this is a 90 degrees ply. So the thickness is within 15 to 25%. So they satisfy the laminate composition constraint. And this is French, this is web, and this is 0 degrees plus or minus 45 degrees, 90 degrees. This is the 0 degrees plus or minus 45 degrees and 90 degrees. They all satisfy the laminate composition constraint. And finally, we want to look at the active constraint of the GBJ-ST. Active constraint are those barely satisfied constraint. Strain constraint are not active constraint. Panel buckling, this is a panel shown by the brown color of the panel buckling constraint are the dominant constraint, and also the stiffness ratio constraint are the dominant constraint. Okay, this is the end of the